Hi, I'm Kevin Keller, the pragmatic statistician. In this episode of Street Stats, we're going to talk about rules of thumb for correlation coefficients, or in today's vernacular, when I went to school to study statistics, I learned that statisticians despise the term correlation. Correlation implies cause and effect, and we know that isn't always true. Now, ironically, they were okay with R squared, which is correlation coefficient squared. Go figure. However, it's a reality that we deal with. If there is true cause and effect, then correlation is useful for us to understand. Where we go wrong is we expect perfect correlation if there is a relationship, and that is simply never the case. As my motto goes, the streets are messy, and so is data. The world is ugly. If we can find a signal in the midst of noise, we need to celebrate. I first learned the concept of correlation in college. I was in a unit operations lab as a chemical engineering student. We had two gauges that we were supposed to measure the same thing. We learned how to do a calibration experiment. We collected information from both. We hand calculated everything back in those days, and one of the statistics was the correlation coefficient. Now, specifically, what we use commonly is the Pearson correlation coefficient. There are others. Now, in a calibration experiment, you want an extremely high correlation coefficient. Otherwise, you would reject the newer gauge as not being as reliable. That is making an assumption that your existing gauge is actually close to the truth in accuracy and precision. But for now, we'll assume that it is. All of our instruction in statistics, intentional or not, convinces us higher is better. And we learn to expect perfection. That is not true, and it will never be the case. There is noise everywhere. And because of this mentality of higher is better, we often dismiss real signals because of their magnitude. So here's my rule of thumb for correlation coefficients. In absolute value, if the correlation coefficient is less than 0.4, absolute value, it's weak to non-existent. If it is between 0.4 and 0.7 in absolute value, we will call that moderate. And if it's 0.7 or greater in absolute value, we will call that strong. Now, I've seen some literature go down to 0.3 in absolute magnitude as the start of moderate. For me, I'm more worried about potential confounding in the data at this point versus a real relationship. Even if I miss something, it's so small, it's likely not worth it. That's me. Pick your pick. At 0.4, you do not have to worry about p-values. I suppose it's possible, but I've not seen a p-value not significant when the correlation coefficient in absolute value is greater than 0.4. Doesn't mean it couldn't happen, just have never seen it. What bothers most people about this table is the value of 0.7 representing the start of strong. They have learned 0.9, 0.95 as being strong. 0.7 breaks their paradigm. What does that look like? Well, let's look. So we're going to go to EngineRoom, and I've got a couple of data sets lined up here. I've got moderate. We'll do strong first. But I created some random numbers and created correlations that are close to these thresholds. So we're going to put in strong here first just to see what does a correlation of 0.7 look like. So here I created a correlation of 0.7173. It's a little harder than it sounds to create random numbers that are exactly zero point 0.7, but you can actually see some sort of relationship as x increases, y increases. And I purposefully did not apply a line, but I can do that. It'll make it just a little easier to see that as x increases, y increases. And I always get my wallet out and I say, does anybody want to bet that there isn't a relationship between x and y, given cause and effect? So, is it perfectly linear? Of course not. We'll deal with that another day. But that's kind of what a strong correlation might look like. What does the start of a moderate correlation look like? Well, let's check that out. So we're going to put in moderate X and moderate Y. We'll click and we'll say, we'll just go ahead and apply a line there just so that we can see it. And you can see that it's barely starting, that as x increases, y is barely increasing. And that's kind of why I say zero point 0.4 is the threshold of, is this really where we start thinking, yes, there's a relationship. And you can see the correlation coefficient up at the top, 0.39. So this is just the start of it. And obviously, as that correlation coefficient increases, things get a little more clear. So now, if, and that is a big if there is cause and effect, then that strong correlation, 0.7, there's a relationship there. Now, here's where the devastating implications of higher R squared is better rears its ugly head. If I square these correlation coefficients, I get R squared. If a correlation coefficient of 0.7 is strong, when we square that, we get 0.49 or 49% R squared. I have seen the following with engineers, data analysts, and senior management. R squared at 50%, that's nowhere close to 100%. There's so much other noise in the process, so you don't have a good model. Again, assuming cause and effect. Time out. Whether or not you like the fact that there is noise or not is irrelevant. There is still a relationship. Again, we are assuming cause and effect. There is a relationship between X and Y, period. End of story. Now, is it perfect? Of course not. But to merely say nothing's there because the R squared is not high is merely crazy talk. It's uninformed and will lead to poor decision making. As long as you choose to listen to my videos, you will hear me beat this drum over and over again. Stop looking for higher R squared is better. It's just plain wrong. I've said it before and I'll say it again. Our good friend George Box stated, all models are wrong, but some are useful. Just because it doesn't have a high R squared doesn't mean it's not useful. Correlation of plus or minus 0.7, and there's a strong belief of cause and effect, you've got a strong signal in your data. Plus or minus 0.4, maybe the start of something. Anything less, masked by a lot of other noise. So be careful out there. The streets are messy, and so is data. But remember, there's always a way.